It's God who's the creator, a creator whose creations may never fail. Mankind has made mega structures, built huge bridges, made deep tunnels, built extreme machines, and conquered the impossible. Yet, the creations of mankind are susceptible to failure. Failure is inevitable in course of time. Designers could do their best to firstly avoid a failure and secondly to make products which may not be fail-proof but certainly are fail-safe. It's very important to understand the difference between the two. In Indian railways, in older times, the brakes used to work based on vacuum. This meant whenever the vacuum failed, the brakes would also fail and the train won't stop. In today's train, the brakes are held in open position using the vacuum. This implies that when the vacuum fails, the train shall automatically stop. All of us agree that a vacuum failure resulting in stopping of train is much better and safer option than the train not stopping at all. In electrical industry, the failures could be disastrous. The impact of the failure is so severe that one has to see it to believe it. Easily, a failure in a medium voltage device could take the life of the operators. As any industry evolves, it becomes more and more aware of the hidden dangers and ways to fight against it. The earlier versions of car did not have the safety guard or the airbags, whereas any modern car can't do without it. Similarly, the international standards governing the medium voltage switchgear have evolved over the last few years, especially since introduction of new version of IEC 62271 series in 2003. These new standards are more oriented towards simulating and testing in the real-time conditions and installations, practical usage, and above all, the safety of the operators has become the highest priority. These changes dramatically affect the customer and even more the operator. Let's take few examples of these changes to see how it affects the safety of the operator. In the older IEC, it was required to perform the internal arc test to see if the enclosure keeps the operator safe. However, the flaw in this requirement was that neither it was simulating the actual installation condition, nor it was testing the worst condition. In reality, the switchgears are not placed in a room whose ceiling is as high as shown in this video. Actual studies indicated that during arcing faults, inside medium voltage switchgear, a huge ball of hot air gases is created, and the enclosure should sustain the enormous pressure applied by these gases. This withstanding of pressure by enclosure saves the operator from facing the fire, so it's nice, but not enough. The life of operator is still endangered due to the reflected hot gases from the roof in actual installations. Hence, unless an actual installation is simulated, this dangerous effect of reflection from the roof remains untested. Thus, the new IEC demands that a room be simulated for testing the internal arc effects. This means erection of side walls, rear walls, and a roof to be erected, and then the medium voltage switchgear is to be placed in this built-up, and then it has to be tested. Another weakness of the old IEC requirement was that it did not specify as to which cubicle should be tested for the internal arc test. This implied that the choice of cubicle was left to the manufacturers. The manufacturer always tested the middle cubicle of a switchboard, claiming to simulate the real-life working condition. However, this method of testing actually protected the enclosure by providing support to it from the two sides. All it had to do was to withstand the pressure on the front door and the rear cover. The side walls were automatically protected by the side cubicles. The new standard demands that the room simulation should be done in a switchboard and may be placed under this simulated room, and only the extreme cubicle should be tested and not the middle one. This means that the cubicle is now not getting any support from the sides and is really withstanding the full pressure which would be required in case of fault occurring in the end cubicle. With these two changes, the situation alters completely, and now the enclosure is really subjected to the worst condition, and if it passes this test, then one gets the guarantee of operator safety even in the worst condition. What advantage a successful withstand of this internal arc test could possibly offer? If the front door of the cubicle is kept open during the operation of the switchgear. This brings us to another example which comes from the fact that the old IC did not demand that the switchgears be tested in the real working condition, whereas the new IC makes it mandatory to simulate the real operating conditions as much as possible. This means that if the door of the switchgear had to be opened for operation of the switchgear, then the safety-related tests like internal arc had to be performed with door open. This indirectly implies that all the operations behind a closed door become a mandatory feature for all the switchgears. This translates into the fact that the operator is safe thanks to the tested enclosure and the door interlocks, which prohibit any operation which is risky to be performed while the door is open. The real-life simulation also means that a potential transformer on top of the cubicle could not be used unless otherwise it's proven safe. By performing internal arc test with the transformers at the top and dummy operator in the operating position. Another example of the changes towards better safety and reliability is the fact that the partial discharge test has been recommended for the sub-assemblies and not only for the individual parts, as was the case with last IC. This means that it's not the individual performance of the component but the whole sub-assembly which matters, as it really does in real-life working condition. How a customer could ascertain if the product in question really meets all the criteria laid down in a standard? The testing laboratories across the world would certify the product if all the tests as specified in the standard have been conducted on a sample which has satisfactorily cleared the test. If not, then a report of performance is given which may indicate that the test procedure followed has been strictly in accordance with the standard. However, the results may be up to the reader to interpret. The simple choice for a customer would be to ask for the full certification from a reliable laboratory. Strict adherence to the latest standard automatically guarantees the safety of operating personnel. Still, there's a catch. Take the example of a door which is very important part of the enclosure from point of view of protection of the operator from arc faults. It may happen that a particular door has been type tested with many screws securing it to the cubicle, but practically unsafe, as in real life situation, any operator would be reluctant to secure too many screws on a part which he may need to open often. The door has to be like a refrigerator door, which could be easily latched. This big difference between theoretically safe and practically unsafe could be life-threatening to an operator. One level of safety is to operate the medium voltage switchgear by standing behind a tested enclosure with practically safe door. This is the minimum safety level which must be attained for the sake of safety of operating personnel. Another level of safety would be to operate the equipment from a safe distance via remote. This is possible to achieve when two conditions are met. A. The circuit breaker inside the cubicle is moved using a motor which could be controlled from remote. B. The relay and the metering cubicle is detached from the cubicle and kept separately from the main medium voltage switchgear. If both these features are incorporated, then it is possible to keep the medium voltage switchboard section in a locked room with secure access and operation by authorized personnel in case of need only. At Areva T&E, it has always been our endeavor to not only abide by the standards but lead the initiatives intended towards bringing much higher level of personal safety and reliability to the user of all our products. These initiatives led us to innovate technologies like solid insulation and solid encapsulation, which make the circuit breaker insensitive to the environment on one end, and on the other hand, we have tested our products for internal arc safety for 1 second duration at international labs. Thus, we are proud to present the fact that our product offering meets or exceeds the highest standard of safety and reliability of the latest standards, making the working safer and better. Areva T&D